recording is rolling. It is Friday, November 8th. So here's top scientists on the last quiz, which was circular motion, gravitation, and orbits. So awesome job if you made this list. I have not handed the quizzes back yet. When I do, of course, you guys can do corrections, just like always. Right, but I'm still waiting on some late quizzes. So here's what I got. I got AP classes, honors classes, conceptual classes. Here's the number of late quizzes from each one that I haven't received yet. So I'm still waiting on some more. Right, because we got a long weekend coming up. So you guys got plenty of time. If you haven't turned that in yet, looking for that. All right. Now yesterday there was a pendulum speed lab. You guys are not doing pendulum speed. Right. You guys calculated it with conservation of energy. Then you guys also measured it empirically with the speed gate. Right. Some of you guys turned that in yesterday, and some of you guys just turned in right now. So I'm still taking that. All right. So I will put those in the grade book pretty soon. All right, today our main focus is going to be this 3-page energy table. You guys got this energy table ready to go? All right, so we're going to finish this. You guys turn this into the grade tray at the end of class, okay? You guys will turn this into the grade tray at the end of class, right? Now, if you were absent one of the days we were going over these, then you can go back and find the video and fill those in, and if you have to turn that in after the weekend, but you'll probably have this finished by the end of class, and I can give you guys more points in the grade book. Okay. Oh. Mark Rober, Pinewood Derby. So I posted that link to Google Classroom yesterday. I'll probably repost it again today. If you haven't watched that yet, then watch that over the weekend, because everything that he talks about in there, he's trying to figure out what's the optimal way to design a Pinewood Derby car, build a Pinewood Derby car. Okay, and his thought process goes through conservation of energy. So it's like exactly what we were doing in class. All right, so really good application of that. All right, guys, Monday, of course, is Veterans Day, so I won't see you guys Monday. But you know what? Tuesday is also a weird day because FCLE testing, and there will be testing in this classroom. So my first 4 classes relocated. What's up with this thing? Yeah. All right, so, guys, I posted to Google Classroom an Excel file that says where you're testing if you are testing. I think a lot of you guys are testing. And if you're not testing, there's another Excel file that says where you're going to be relocated to. Here's my own classes relocated. Okay. All right, so you guys go with FCLE. All right, so that's going to be Tuesday. Whoops. All right, and then the next real school day, I guess it's going to be Wednesday, so not for a while. All right, so you guys go with what's going on in the next few days. All right, so we're going to take today to finish that 3-page energy table, and then I'll have a little bit of time left over to, well, we'll see what after that. All right, so the last one we did was, okay, it looks like we got this setup started anyway, is this block spring earth system. All right, now you guys remember the thought process for this energy, conservation of energy, is that energy can take these different forms, right? Energy is conserved, so like the number of joules is constant. In a closed system, that would be true. In a closed system, you cannot create or destroy energy, but maybe you're changing from one form to another form. So if you had a block pressed against the spring, that would be this form of spring potential energy called 1/2 kx squared. If you plugged in numbers for that, like, oh, spring is like 100 Newton per meter, and I squashed it by like 10 centimeters, there's some number of joules associated with that, right? And then where did that energy go? So I have a frictionless track. It goes, pew, flies around this looping up here. So some of that energy went into lifting the block against a gravity field. That's your MGH. And the block has to be in motion to get to that point. So that type of energy is called kinetic energy. That's your 1/2 mv squared. So all you have to do is, here's your equation bank. You just pick equations from here. All right, and that, I think, is where the bell is ringing a couple of days back. And so let's solve this, and then we'll move on to the next ones. All right, so, all right, math time. All right, let's solve in terms of variables. It's a good skill to have. And then, guys, once we get an equation also, is we can step back and look at it and think, what does it mean? Like, what if you change this variable? How would that change this other variable? So let's do a closed system. Sum of energy initial equals sum of energy final. Okay, we got the setup right here. It starts off as all 1/2 kx squared. All the energy was in the spring. And then by the time it gets to point B, some of the energy went to lifting the block against gravity. There's your MGH. And you had some energy left over for motion, and that's 1/2 mv squared, right? Okay. So I have 3 energy terms, right? And if you plugged in numbers, there would be some number of joules. Let's do a quantitative example real fast. Okay, suppose this 1/2 kx squared came out to like 100 joules, right? 100 joules, right? And suppose it took 30 joules to lift it this height. You do mg and h because this comes out like 30 joules, right? 100 here, 30 here. How many joules would be left over for motion? 100 equals 30 plus 70. Yeah, right? Right, 30 plus 70, right? And then furthermore, suppose I told you whatever mass was flying around saying, pew, you could just plug that in, and then you could solve for how fast is it going, right? So that's how this works, right? Let's solve that in terms of variables, though. You guys ready to go on a variable adventure? All right. Let's see. Algebra. You guys ready for some algebra? I bet you guys probably did this for homework anyway, so you guys just checking your work. Just make sure you did this right. All right, I'm going to subtract over the MGH. So got 1/2 kx squared minus the MGH. Right. That gives me the 1/2 mv squared. Right. Trying to solve for this v. Right. Subtract there. Right. Ooh, I can multiply both sides by 2. So that'd be like kx squared minus 2 mgh. You guys did that, right? Okay. Because I got 3 terms. If I'm multiplying something, I have to multiply it by all 3 terms. That leaves me with mv squared. Right. I could divide this mass down. Again, I'm trying to isolate this v ultimately. Guys, does the mass completely cancel out of the equation? No, because the spring constant, the spring energy had nothing to do with the mass against it. It's just however much was the spring squash and how stiff was the spring. So there will be an m in the final equation. I'll divide the m down. I have to divide the m across all 3 terms. But it's still here. It's still here. Right? So I got a kx squared over m minus 2gh. Okay. And that's v squared. Okay. Now, if I want to solve for v, guys, what's the last algebra step? Square root. Yeah, that's right. So v equals, right? So I got a big old square root. I got a kx squared on m. Right, and then minus 2gh. All right. All right. Is that what you guys got? Is that what you guys got when you did? Yeah. All right. Right, it is. All right. So, all right. Now let's read the music of this equation. All right. How can you interpret this? So, I suppose you have you run this experiment, and then you go back and you just replace the spring with a stiffer spring, and you squash it exactly the same, and use the same mass flying around the whole deal, but you just have a stiffer spring. Is it going to be moving faster or slower? Faster. Yeah, because this k, guys, suppose the k is like twice as much, got twice the stiffness. This is going to be a larger number. Okay, so it has to be a larger number for the speed. I think that makes sense too, right? Like if you have a little weak spring, it's like hardly goes anywhere. You have a stiff spring, let it go, it's gonna fly around faster, right? That's exactly what the equation says. Suppose you have a larger mass. What if I had this mass go around, and I replaced it? Hey, now it's my turn to go. Is that gonna be going faster or slower? Slower, which is also what the equation says. Look, if you plug in a bigger mass here, now I'm dividing by a bigger mass. Now it's gonna be going slower, right? In fact, guys, if this mass is too big, and I subtract off 2gh, is it possible that this inside expression might go negative? And then I cannot even take a square root of negative. And what that means is that this might not even make it up there at all. Might be just like not even get there. Okay. How about, what if I make the height higher? Like here, let's go back to the picture. Right. What if this was like 10 centimeters, and then go back and I make this like 20 centimeters, and then 30 centimeters. So I'm making this height bigger, bigger, bigger. Right. What's happening to the speed at the top? It's getting what? Faster or slower? Show of hands. How many of you guys think if I make this taller, it's going to be going faster up here? Who says that? How many of you guys think if I make this taller, it's going to be going slower up there? Yeah, that makes sense, right? In fact, it might not even get up there, which is also what the equation says too. If I make this h bigger, 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 now I'm subtracting off more from this, right? If I subtract too much, this might, even go negative, and the calculator blows up. Right? Yeah, that's how math works. You can't take a square root of a negative number, right? Right. Okay. Right. Yeah, I. That's right. Yeah. So if I like square root of -2, what's that? Domain error. You fail. All right. So you guys got the math here. You guys got v equals, got a square root, kx squared on m, and then minus 2gh. Interesting. I see another 2gh popping up underneath another square root. That seems pretty common in this unit. A bungee jumper dives off a platform and barely touches the ground before the cord boing retracts. You guys imagine that? This guy's on a bungee cord, goes flies off, and then he's going down, and then just as he's about to hit the sidewalk, he reaches down and boop touches the sidewalk, and then the cord goes boing and pulls it back up. Okay. So I need to pick some point A, some point B. Say point A is the edge of the platform, and point B is right. We just beep, touch the sidewalk. Right, so that's guys, what are you going to put in the closed system? Yeah, the Earth. Right now, I definitely need the Earth because there's a gravitational force pulling this guy down, and there's a height change. That's why the Earth is part of the closed system. What else? Yeah, the jumper, the bungee jumper. It's like right, and also the bungee cord. That's right. Because at point B, I think that's where all the energy goes into like stretching that bungee cord, doesn't it? Okay. Right. So, what type of energy at point A? Potential energy. I definitely need some MGH going on. Right. Oh, now here's where you can interpret this one in two different ways, and I don't care which way you did. Like, if you solve this for homework, whichever way you did this, so okay. If you say it's just potential and you just go to the edge and it just like steps off, then that would be all that you start with MGH. Okay. But I threw in the word dives. Guys, if this guy's like super energetic, it's like, I can't wait to jump off. And he does like a running jump. Whee! Then he also has what type of energy at point A? Kinetic. So you could have interpreted it this way. Plus 1/2 mv squared. A little bit more complicated. I'll solve it that way. Again, if you didn't do that for homework, that's okay. If it gets down to point B, where'd all the energy go? He has no more height. He has no more gravitational potential energy. Where'd the energy go? I'm looking for spring potential. Yeah, spring potential. Okay. And wait, where's my checklist? Here's my checklist. Okay. So that looks like, oh, that's this one right here, isn't it? Right here. Okay. So that's 1/2 kx squared. Okay. Can I say equals right here? This plus this equals this. Right. That would be a closed system. Yeah. Okay. Guys, next question. Is this X and this H the same thing? Yes or no? Here, show of hands. What do you guys think? You guys know what H is. It's the height difference between A and B. Okay. Guys, is this X and this H? Are they the same thing? Who thinks they're the same thing? Who thinks they're different things? Yeah, I think they're different. Here's why. Because this X is how much the cord was stretched. I think that cord probably had some original length. But like I suppose the cord was like, here, I'm gonna make up some numbers. Right. What if this height was like 100 meters? 100 meters height? What if the cord itself was like 50 meters long? If the cord unstretched was 50 meters long, and then you stretch it an additional 50 meters, then this X is just how much it was stretched, right? But beyond its unstretched length. Okay? Right, which is gonna be less than that height. All right, let's solve this out in terms of variables. Sum of energy at point A equals sum of energy at point B. We got some MGH at the top, plus possibly a 1/2 mv squared. Right. Up to you whether you want to interpret it that way or not. Okay. But at the bottom, it's all 1/2 kx squared. That's where all the energy went. Oh, you know what? Never mind. What are we even solving for? Guys, what are we trying to find? The speed of point B? Guys, what is the speed of point B? Huh? 0 meters per second. So oops, right. I forgot what we were even trying to solve for. Yeah, there is no speed at point B. Okay. Might be a speed at point A, maybe if he's doing a run and jump. Okay. Okay. So you could still solve for stuff. Like here, guys, you could solve this. Like, what if I know how tall the cliff is? I know how fast I want to run. I know my own mass. I know the gravity field, and right. Maybe I want to solve for what bungee cord do I need so that I don't die. Ooh, I might want to solve for what does this K have to be? Okay. I hope I buy the right cord so you can solve for that. All right, next one. Hey, actually, these next couple are some Atwoods. Ooh, I see some Atwoods. And both of these you guys have done lab versions of. Well, sort of. You guys remember way back in the day, these Atwoods? I had you guys do, it was 2 halves of a lab. I was having you guys solve for the acceleration at the time. And that was the whole lab, just solve for the acceleration. Okay. Now, once you have the acceleration, you could answer other questions like, how fast does it move after some time? How far did it move after some time? How fast is it moving after some distance change? right? Those are all kinematic questions after you get the acceleration, right? But now we have a brand new way of thinking about these Atwoods. Here. Right. So I got, here's the next couple questions right here. I got the classic Atwood right here, right? And I got, well, this isn't exactly WitchCat, but here's a modified type Atwood, right? So we got kind of both of these going on, right? And so what's the new way of thinking of it? Let's go through this. So what did you guys put in the closed system? M1, M2, and the Earth. Aha. M1, M2, Earth. Okay. Okay. Now, a couple of objects that I did not include. I did not include the string because the tension is just internal to the system. So whatever, that didn't really matter, right? I also did not include the table surface. Now, there is a force from the table surface. It's a what kind of force? A normal force, right? So it says there's no friction, but there is a normal force. But if you're sliding parallel to the surface and the normal force is perpendicular, guess what's the dot product of two perpendicular vectors? Zero, right? So the normal force never does any work on the block. That's why you don't have to include the table surface. All right, it's a little technical detail, but in case you ever see that. All right, what type of energy at point A? Aha. And how did you guys write the formula for potential energy for here? M2GH, right? Specifically, block 2 is about to fall. The fact that block 2 is elevated and can fall is about to fall to a lower height, that's like supplying the potential energy, supplying the energy. Right? By the time this block 2 does fall to position B, where did all the energy go? Huh? Well, we'll say it just still on this table surface, so it didn't change height itself. True. Tell you guys what. Could M1 also have potential energy? Could I say plus M1GH here? I could, but if I did, then by the time it gets to point B, it has the same M1GH, so it just cancels out anyway, right? That's why you don't even have to write it. Okay, that is a good thought though. Right. But where else could the energy go then? Here's your options. Kinetic. Isn't it true? Here guys, let's say point B is like 1 millimeter above the floor. So basically the height's gone. But I bet this block has a speed. I bet this other block has the same speed because it's connected by the string. Right? So is that 1/2 mv squared plus another 1/2 mv squared? Except here could be maybe block 2 and here's block 1. Okay, something like that. And I can say equals. Okay. So, big picture, suppose I gave you some numbers, you plugged it in. What did this M2GH came out to like 100 joules? I'm just making something up. Looks like 100 joules, right? And what if they were the same mass? Then this could be 50 joules here, and this could be 50 joules here. You guys got that? Okay. And then, or if they're not the same mass, then it might be like 40 and 60, or it might be 30 and 70, or 80 and 20, but they would have to add up to the original number of joules. That's what conservation of energy is. Right, let's solve for this V. You guys ready to solve for V? So sum of energy at point A equals sum of energy at point B. Or I guess you're really checking your answers, right? So M2GH goes to 1/2 mv squared plus another 1/2 mv squared. Only they're possibly different masses. So let's do mass 2 and mass 1. Right. But guys, even though they're different masses, do they have the same speed? Yeah. Right. Now, maybe different directions. One's going down, one's going to the side, but that doesn't matter. The direction of motion does not matter for conservation of energy. If you guys notice, where energy is like a scalar value, it doesn't have a direction associated with it. We're just quantifying how much energy in joules. Right. So, all right. So what we're gonna do? Yeah, multiply by 2. Right. Now, guys, how many terms are there algebraically? 3 terms. Point. I got 3 terms. So if I multiply by 2, do I have to multiply every single term by 2? Yep. So 2. I got 2 M2GH equals, while I'm at it, since this V is the same, can I just factor out the V squared? And that would give you M2 plus M1. And I can pull the V squared out, right? Is that okay?
Would you cancel out M2 or no?
Okay, no, the masses don't cancel out because right, it's different masses in the terms. Like I have 3 terms and they're different masses.
Oh, okay.
Possibly, right? Now, if I knew they were the same mass, or even if I knew the proportion of the mass, then I could sort of cancel them, right? But I don't know whether it's M1 compared to this M2, so I have to leave it together. Right? Now I can divide this over. So I got well, 2 M2GH, right? And then divide by the sum of masses. Right? But still nothing cancels out because I have things added together, grouped together, being divided, right? So nothing cancels at this point. Right? What's the very last step? Take the square root. There you go, square root. Got 2. All right, so the falling block mass up here, GH, right? And then divided by the sum of the masses. Just like that. Okay. All right, that should be the answer. Right. Notice how I wrote my answer and how I did not write my answer. You guys say this? Okay, I got a square root, I got a 2, got an M2, a G, an H, and divide by, and then M2, and an M1. You guys, did I write it like that? Is that the same thing? No. So when you're writing your algebra equations, make sure it's really legible, like what you're dividing, what you're taking the square root of. You guys see that I very clearly have the M1, M2 all grouped together in the denominator, right? Okay. I didn't here it's ambiguous. It's like, wait, is the M1 outside? Is it inside a fraction? I don't really know, right? And also, guys, my square root bar clearly extends over the entire fraction, and it's also tall enough to cover the entire fraction vertically, right? Both vertically and horizontally. It's like a little box here, right? Versus here, it looks like I'm not taking the square root of it. Okay. Right. I'm really emphasizing that point because I'm seeing lots of papers, over the past years and this year where students kind of like shortchange their square root sign. Okay. All right. So there's your answer right there. You guys got a square root, whoops, b equals. You got a big old square root, got a fraction, 2 M2GH, and then divided by the sum of the masses. The square root of all of that. Right, just like that. Wait, I did have a poster on that. Is that the same answer on my poster? Oh, my poster just has the setup. Sorry, that's not even the right one. That's the next one. We're about to do this one. Okay, whoops. And this one's a little bit different anyway. All right, because I included friction on that other one. All right, so last thing about this one is let's play around with this formula a little bit because I want you guys to, one of the things I want you guys to get from this class is to be able to read the music of these equations, right? So, like, what if you change some variables? How would that maybe affect something else? Like, what if, let's go back to the picture so I can point this out. Okay. What if M2 was really heavy compared to M1? Like, what if M2 was like this guy, right? Like 1 kilogram, and M1 was like a little tiny paper clip. And you release it. How much is this going to accelerate down? Almost. Guys, I got M2 is like a kilogram. I got M1 is like a little tiny paper clip. How much is this going to accelerate? Almost. How fast? Is it infinity fast? Is it the speed of light?
No.
How fast can it accelerate? Aha, 9.8 meters per second squared, right? Maybe it's a tiny, tiny less than that. Maybe it's like 9.79 meters per second squared, right? But it can approach free fall gravity, right? You guys see that? So is that what the equation says? Let's see, how does that show up in the script? So I said M2 much larger than an M1, right? So let's say proportionally this M1 is very tiny compared to this M2. Numerically, that's close to 0, right? Right. Let's let M1 go to basically 0. Oh, if M1's 0, does the M2 at that point actually cancel out? M2 over M2? Yeah, it does. Oh, and look what that leaves you with. Look at that. It's square root 2GH. Where have you seen square root 2GH? Yeah, all over the place, including Galileo dropping a ball off a tower. It was square root 2GH, wasn't it? You see that? Pretty good. Okay. All right, next one. We got a classic Atwood. What do you want to put in this system for the classic Atwood?
M1.
Yeah, M1, M2, and the Earth. Probably stands for 4, right? So M1, M2, Earth. Okay. What are you gonna put for the supply of energy. Yeah, M2GH. Right. Again, just like before, the fact that the large mass is elevated and is about to fall. Okay. Okay. Where does that energy go by the time it gets to point B? Okay, kinetic energy. Yeah. So I bet each of those blocks have a motion. So it's like 1/2 mv squared for block 2 plus another 1/2 mv squared for block 1. Right. Wait, I think I'm forgetting something. What am I forgetting? There's one other place the energy goes.
Does M1 have potential energy now?
Ah, that's right. That's what I was forgetting. Yeah. I have to lift block 1. Yeah. That's right. Right. M1 GH. Yeah, and then plus those kinetic energy terms. So that's 3 places the energy goes. Okay? So the large block falls down. That does 3 things. It lifts the small block. So M1 GH, some energy goes into lifting the small block. And then you have some energy left over to give each of those blocks a speed. In fact, they have the same speed. Okay, just opposite direction. That's all right. Okay. I think that is what I have on this poster. Where poster? Here, poster. Here you go. Hey, that's it right there. Look at that. That's exactly what you guys just wrote, isn't it? That's the setup. Okay. Now all we got to do is solve it. You guys ready to solve it? All right. Let's solve. So sum of energy at point A equals sum of energy at point B. We got M2GH falling. That's going to lift block 1. So M1GH, some energy goes there. And I got a 1/2 mv squared plus another 1/2 mv squared. Now this is block 1 and this is block 2. It could be, right? And let's say we're solving for this V, the speed at point B. Okay. All good. Right. Well, maybe I should. Okay. Do you guys see I have how many terms? How many algebra terms? 4. 1, 2, 3, 4. You guys see it? Right. So maybe I should subtract this one over. And while I'm at it, I'll factor out the v squared on the right side. Right. Yeah, I can do that too. Yeah, I can multiply by 2. Right. Actually, let's do that first. Why not? Multiply everything by 2. So I got 2 M2GH equals 2 M1GH. And then plus M1V squared plus M2V squared. Okay. So multiply everything by 2. Yeah, subtract this over. So 2 M2GH minus 2 M1GH equals, right, and then over here, got an M1 and an M2, and I could take the V squared out. Okay, so at some point it looks like that. Right. Oh. Right, on the left side, I see a 2 and a G and an H all in common. Can I factor all that out? Right. So that'd be like a 2G, interesting, 2GH is showing up again. M2 minus M1, and that's equal to the sum of the masses M1 plus M2, and then V squared. Right? All right. Checks out so far? So what you guys were getting to? All right, so I got 2 algebra steps left. I think I'll do them all in one step here. I'm going to divide the sum of the masses over, and then take the what? Square root. That's right. So V equals, right? So see, if I divide this over, I got 2GH, difference of masses over the sum of the masses. And then the last step is square root of that entire expression. Okay. Is that what you guys got? All right. I'm gonna write that in this little box right here. So speed at point B equals big old square root 2GH, difference of masses over sum of masses. There you go. Okay. Right. Now, while you guys are finishing that, or checking your answers on that one and digesting that one. Right. So recap on Atwoods. You guys saw Atwoods many weeks ago. I had you guys solve for the acceleration. Once you have the acceleration, you could kick back to kinematic motion, those 3 kinematic formulas, and answer lots of other questions, speed questions, height questions, time questions. Right. Now there's the new method with energy conservation. And we just solved for the speed at the end of some height change. Because this right here is the ideal question for Atwood's if you want to solve it in terms of energy, right? So if you open up a physics textbook to the energy section and you see an Atwood, but almost guaranteed they're going to ask this question, is what's the speed after some height change, right? Notice what variables I have not mentioned at all for these Atwoods. I haven't mentioned anything about time. I haven't really mentioned anything about acceleration either. And time and acceleration, you were definitely working with a few weeks ago with Atwoods, right? With those equations, because this is an entirely different way of thinking about it, right? But kind of like the car braking to a stop. You guys remember the other day we solved it two totally different ways, but got the exact same braking distance. Right? Same thing. Is you could also solve this question. You know, what's the speed after some height change through dynamics and kinematics, and you would get the same answer. All right. All right. Moving on. Got that. Ooh. These next two look pretty similar. I got a spring fires a ball vertically to some maximum height. And then the next one, a block falls from some height and squashes a spring. Okay, great. So one at a time here. What do you think is going to be in the closed system? Okay, yeah, definitely the spring, the ball, and the earth. Yeah. Right. I'm focused on the ball because see, it was changing motion itself at some point. The spring because the energy's in the spring at some point, and the earth because there's a gravity field and a height change. Right. Good. All right. So what type of energy at point A do you think? Exactly. Got some 1/2 kx squared going on. Okay. By the time it gets to point B, what type of energy?
Is it just regular potential because it's like up in the sky?
Yeah, just regular potential energy, MGH. That's it. There you guys. Okay. Can I just say equals right there? Okay. Yeah, right. And ooh, guys, what is the speed at point B? 0 meters per second, right? Right. So your textbook probably wouldn't even ask that question. They'd probably ask something like how high does it fire? Which, by the way, is a short lab I want to do with you guys next week. I don't have this designed yet, but I got these little poppers. I just fold this inside. Did I do a popper with you guys the other day? Right. Here, if I put this down here and let it go, pow, like it's gonna go some height. That's kind of it's kind of like what we just did, right? So if you turn this little dome inside out, it's kind of like a spring, and it pops at some height. Think about it like that. Okay? Oh, right. This next one looks really similar. It says we've got a block that falls from some height and squashes the spring. Do you think it could be the block? I don't know what's called a block, whatever. The spring and the earth, right? Like block spring earth system, like before, right? Except it's doing the opposite. It started at some height. So what kind of energy right here? Yep, MGH. Support A. Okay. And what kind of energy would it? Let's say it maximally squashes the spring. What kind of energy? 1/2 kx squared. Oh yeah, right. I could say it equals right there, right? Okay. And what's the speed at point B if it squashes it maximally? Yeah, 0 meters per second. That's a good assumption. Right. I know this is a really brief blip right here. If it was in a textbook, they might add some details to that, so you could kind of confirm that would be true. Right. I think if you took a video of this and let the clock run forward, it would do something like this. Boing, and it would probably like change direction and bounce back or something like that. But we're not gonna worry about it. But there's another detail I want to think about this one because guys, these questions. Well, actually, a couple of details. Do you see in parentheses here? I said assume no mechanical energy loss during collision. I'll tell you what that means. That's something that we haven't talked about in this class, but we'll do a couple of weeks from now. Whenever you see objects colliding, like two blocks colliding, or like a bat hitting a ball or something, the process in physics you want to use is conservation of momentum. We haven't even talked about that yet. Momentum is just mass times velocity, but we will eventually. But whenever you have something colliding with a spring, it's really common in a physics 1 class to say, well, assume the spring has negligible mass compared to, say, the block colliding with it, in which case you can bypass all that conservation of momentum, which we'll do in the future in this class. And then you can just solve it with conservation of energy. So basically this right here, you just do this, right? Right. The other detail I want to do is, do you guys think while this block is squashing the spring, and this could have also applied to this last one, right, that could be considered part of the height change, possibly? Right. So let me give you guys the more nuanced version of this, because this is something I saw in college. And if you guys take physics in college, there's a good chance you're going to see exactly the more nuanced scenario I'm about to give you guys right now. say you have this block, mass M. I got this spring. It's got some spring constant K, something like that. And maybe the block started off with some height above that spring. Okay. And then sometime later in the system, here comes your block mass M. It squashed the spring. All right, got K. Okay. How much did it squash it? Squashed it some amount X. Right, something like that, right? Okay. Now, if I set up this conservation of energy, sum of energy initial equals sum of energy final. Okay. Oh, do you guys see that while the spring is being squashed, like gravity's still pulling it down? And so it's like, how do I define this height? Okay. Now, on your paper, I guess you could think of it this way: you could define this whole thing as the height, and it would be exactly the answer on your lab page, right? But if the height is only to the top of the spring, then the potential energy would act, gravitational potential energy would actually be this. It'd be m, g, and it's not just h, it's actually h plus x. And then that's actually what goes to 1/2 kx squared, right? In fact, if you actually wrote that, what I just wrote right there, if you wrote that on your energy table, I would accept that too. It's just a different interpretation of it, right? All right, next one. Ball rolls without sliding down hill length L. Now, this comes from a future topic of physics, so it's kind of a challenge question, but yeah, we'll do this anyway. So first of all, if it's rolling without sliding, do you guys think there's some static friction that's going to induce rolling? Some static friction could induce rolling, right? Because if there was no friction, it would not roll at all. So you need friction to induce what's called a torque to make it roll. Okay? But interestingly, that friction is not actually taking energy out of the system, because at a glance, you might say, hold on a minute, that reminds me of something. Hey, isn't that kind of like the kid in the sled, sort of? And weren't we treating that as an open system? Wasn't the friction doing negative work on the kid in the sled and taking energy out of the system? And that's all true. But that's not true for rolling. Right? All the friction force is doing is just inducing a torque so it can roll. Right? So we can still treat this as a closed system. Right? And some other, well, here, we'll start with that. All right, got some other things I need to tell you guys. What do you guys think is going to be in the closed system? What objects? The ball? The earth? Right. And I'm going to throw one more object in the system. The hill. Yeah. Right. The reason I'm going to include the hill in the closed system is because that friction force would otherwise be external to the system. But if I include the hill, then it internalizes that force. Okay. Right. Again, the force is not doing negative work. It's just inducing a torque. Right. So what type of energy at point A? Aha, gravitational potential energy. There's your MGH right there. Right? Okay. By the time you get to point B, what type of energy? Kinetic. Right. So here's what I'm going to call translational kinetic energy. 1/2 mv squared. Right. That's like if either you point a radar gun at the ball, or if you had one of those speed gates, like from your lab yesterday, and it zooms through the speed gate. That's what that V is. Right. But guess what? That's not the entire story. Guys, watch this. Say plus, because there's still one more place the energy goes. Actually, here, let's show you guys your options. Here's your equation bank right here. Which one of these 6 expressions does some of the energy also go into? And we haven't touched it yet. Boom! Rotational kinetic. You guys see this green one hiding right at the very bottom? 1/2 I omega squared. All right, you guys see that? There's some energy that goes into making it rotate, right? Or if you want to be really tricky about it, do you think you could take this ball, split it up into like a billion different points, and say, well, each individual point has a linear kinetic energy. You can do like 1/2 mv squared for like a billion points, something like that, right? But that gets really, really, really tricky. So there's a more consolidated way to do it, and that's just with one term, 1/2 I omega squared, right? So say plus 1/2 I omega squared, right? Now, this is from the future. So this is a future topic. We'll probably have to say for January, I'm thinking. Right. Here we go. Let me show you guys what some of the stuff means. You guys see this I right here? So if you have different rolling objects, like the cylinder rolling has some rotational inertia associated with rolling. If I have a cylinder next to a ball, suppose they have the same mass, and I kick them, boom, I put the same force on them, right? I'll feel effectively a different inertia from them, right? Just the fact that by the fact that the mass is distributed differently. Like a cylinder is a different shape from a sphere, right? So here you go. Here, you guys gonna see this in the future in this class. So, I is proportional to the mass, right? So how much rotational inertia does it have? That's what this is, rotational inertia, okay? But it also has to do with how's that mass distributed. So something to do with like r squared. So it could be mr squared for like these, right? Oh, here's a cylinder, right? Here's here's a solid ball rolling. Here's a spherical shell, like a basketball rolling, right? And they're all a little bit different, right? So just for today, just for this table, we're just going to call it I, right? Just very, very generically I, right? All right. So how are we going to solve this? We'll still solve it. So sum of energy at the top equals sum of energy at the bottom. Okay. We got mgh at the top turning into, yep, there's some 1/2 mv squared going on. There's also some 1/2 I omega squared going on. And that I depends on what kind of ball it is. If it's a basketball or a bowling ball, that I is going to be a little bit different. Today we'll just call it I, right? Okay. But you know what? You guys do know this omega. I gave you guys this hint. You guys see this hint right here in gray ink? This is something that you guys already know, right? Guys, what can I substitute in for this omega? V over R, right? V over R. R being the radius of the ball. So let's do that. mgh equals 1/2 mv squared plus 1/2 I, and instead of omega, I would call it v over r, and then square that. Okay, so that could be like look like this: 1/2 mv squared plus 1/2 I. Okay, I got v squared over r squared. That's what that could be, right? Okay. Now, if you want to solve for this v, we can do that. All right, you guys ready for some algebra to solve for the v? All right, so let's multiply everything by 2. So it could be 2 mgh equals mv, I'm solving for squared, plus I over r squared times v squared. Give you that, right? Okay, I could factor out the v squared. So 2 mgh equals, and over here I'll have m plus I on r squared, then times v squared. Okay, divide both sides by this fraction, or this grouped in parentheses, I should say, right? And then take the square root. So the speed at the end is, it's going to be a square root. I got this 2 mgh here. Then divide by all this stuff. Got an m plus I over r squared, just like that. Right? That's how fast. It's the algebra to finish that up. Right? What should I say here? Okay. Okay, so then if you know what kind of ball it is, you could just plug that in for the I. Okay. Now I do have another poster here. This is specifically for basketball. This is always the answer. Okay, and look at that answer. It's not exactly square root 2gh. It's got to be slower than that because some of the energy went to making it roll. And for basketball, it happens to be like this, right? But it's the square root of something times gh, so it kind of follows that format, doesn't it? All right, last one. Get ready for last one. So 2 asteroids. Call us each asteroid. Here, we'll finish this right here. I'll have you guys turn this in before you leave today. It starts off with negative g m m on r. We're going to use that universal form of gravitational potential energy, this green one right here, because gravity field's changing as they get closer. Okay, and then and that's r a. By the time it gets to position B, that's negative g m m on rb plus a 1/2 mv squared for one asteroid plus another 1/2 mv squared for the other asteroid, also in motion. So they start at rest, then they get closer together, and they're now in motion. So they have some kinetic energy too. Okay, go and do that. If you guys do that, then you're good to go. Turn that into the grade tray. Turn your packet into the grade tray, and I will give you guys some points in the grade book. All right, and that's a wrap on today. I'll see you guys on Wednesday.